Welcome back, everyone. Today we shall continue with lecture one. The two previous sections, I did a review on real numbers and basic algebraic structures. For the review parts, although you were not responsible um, in any way, you still need to review and know those notions. And as part of the review, you need to actually do assignment number 0 and assignment number 1 in MyLab. One deals with how to use MyLab, and the second one deals with the properties of real numbers and the basic algebraic structures as we reviewed the last two times, or the last two sessions. So today we'll talk about equations and their graphs. I'll start sharing the screen and writing and making notes. Bear with me for a moment. Okay. All right, I'll share the screen as before. Okay. So as I said a minute ago, we'll talk about equations and their graphs. All right, so this topic pertains to section 1.1 in the book and assignment number 2 in MyLab. So what is an equation? I mean, you have seen equations before and you know how to solve various equations from college algebra, you know how to factor. So it's not the first time you see equations. The purpose of this lecture is not to go over the various methods that you know of solving various equations, but rather to talk about equations and their graphs or their graphical solutions. But first, let us briefly and loosely define what an equation is, give some examples of equations and common equations, and then we'll talk a little bit about the graphical part of those. Okay, so definition. An equation is basically a mathematical expression that contains an equal sign. So an equation is a mathematical expression that contains an equal sign. This, an equal sign. All right, so here are some examples of equations. Y equals to 3x plus 5. Y equals to absolute value of x minus 3 plus 7. Y equals to x squared minus 2x. Y equals to the square root of x plus 3. Y minus x squared equals to 16, and so on. So these are various examples of equations, and specifically we can talk about some very common equations that we have seen before. So common equations. Y equals to x is probably the simplest of them all. Y equals to x squared, y equals to x to the third, y equals to absolute value of x, y equals to the square root of x squared plus y squared equals to 49, and so on. All right, so as I said a minute ago, the aim for this lecture is not really to remind you or learn how to solve these different types of equations, but rather to talk about their graphic representation or their graphic solutions, or otherwise known as their graphs. So before we talk about the graphs of an equation or graphs of equations, we first need to introduce the so-called Cartesian plane. So to talk about the graph, a graph of an equation is basically a bunch of points on a plane in a two-dimensional space, that is. So a collection of points connected together make the so-called the graph of an equation. So these are not just any random points, but where these points are on the Cartesian plane or on this two-dimensional space, or how you plot them, where do you find them, and where do they come from, it all depends on the equation that we're dealing with. So before we talk about the plotting of those points, let's talk about the Cartesian plane. The Cartesian plane actually is a two-dimensional space, and a point in this Cartesian plane or this two-dimensional space is identified by two coordinates. So what are these two coordinates? I'll tell you in a minute. So Cartesian plane is just the plane. It's a simple plane or simple two-dimensional space. And in it, you may imagine the copies of two real lines perpendicular to one another. So here is a vertical real line, and here is a horizontal real line. These are nothing other than two copies of the real line that we talked about during the review. So these are lines of real numbers, two copies being perpendicular to one another. The point at which these two uh, real lines intersect one another is where we identify the origin of the Cartesian plane, or the point 0, the point with coordinates 0, 0. So these two real lines that are perpendicular to one another divide the Cartesian plane in 4 quadrants. This is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. The horizontal real line is the so-called x-axis, and the vertical real line is the so-called y-axis. So we will identify a point in the Cartesian plane by an x-coordinate and a y-coordinate. In the x-axis, you have real numbers. To the left to the right of 0, you have all positive real numbers. To the left of 0, you have all negative numbers. In the vertical y-axis, to up 0 and up, we identify the positive real numbers, and on the bottom, negative real numbers. Okay, so having said all that, All the numbers that will reside, so to speak, in quadrant one, their coordinates will come from this part of the x-axis and this part of the y-axis, meaning from the positive part of the x-axis and the positive part of the y-axis. So here you'll have positive x, here you'll have negative x, here we'll have positive y, here we'll have negative y. Negative y. All right, and where they intersect is 0, 0. So in quadrant one, we'll have all points that have a positive x coordinate and a positive y coordinate. So in quadrant one, the first coordinate is positive, the second coordinate is positive. In quadrant two, we have negative x's, positive y's. So in quadrant two, we have negative x's, positive y's. By the way, whenever we talk about a point in the Cartesian plane and we want to list its coordinates, the first coordinate that we list is the x coordinate and the second coordinate we list is the y coordinate. So the coordinates is a pair of number. The first one is coming from the x-axis and the second one from the y-axis. So the first one is the x coordinate, the second one is the y coordinate. So in quadrant three, the x coordinate, as you can see, in quadrant three is negative, and the y coordinate is also negative. So the first coordinate is negative, the second one is also negative. And in quadrant four, as you can see, the x coordinate is positive, and the y coordinate is negative. Okay. All right, so how do you point? As I said before, a point P is identified by the x coordinate first and the y coordinate second. Okay, so how do we plot now points in the Cartesian plane? Points in Cartesian plane. Okay, so to find the address or the coordinates of a point, so for a point xy, first to plot, or rather to plot point P with coordinates xy, first we move along x-axis by x units, either to the left or right, depending on x. Depending whether x is positive or negative. Is positive or negative. And then we move up parallel to the y-axis, either up or down, and then we move vertically parallel to the y-axis. by y units, either up or down, depending whether y is positive or negative. Depending. If y is positive or negative. Okay, so let us do some examples. We want to plot the following points. Point P1 with coordinates minus 3, 1. Point P2 with coordinates 0, 3. P3, I'm sorry, with coordinates 5, 2. P4 minus 2, 0. And P5 minus 3, minus 4. Okay. So let me draw the Cartesian plane first. Okay. So 1, 2, 3, 4, 5, 6, 7, so on. Minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, so on. These are the x-axis, 1, 2, 3, 4, 5, 6, 7. Minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. After all, these are nothing other than copies of the Cartesian plane of the real lines being perpendicular to one another. So as I said before, this would be 1, 2, 3, 4, 5, and so on. Minus 1, minus 2, minus 3, minus 4, and so on. All right, point P1. First, we move minus 3 horizontally along the x-axis. Since minus 3 is a negative number, the negative axis lie around, meaning lie right here. So I'm going to move 3 units to the left of 0 horizontally, because again, I'm dealing with minus 3. So 1 unit, 2 units, 3 units, minus 3, and I will move. The y coordinate is 1. 1 is a positive number. It's a y coordinate. So I have to move parallel to the y-axis, vertically that is, but up, because that's where 1 is. So minus 3 parallel to the y-axis, but up, is where I locate point P1. Okay. Point P2 is 0, 3. So the x coordinate is 0. I don't move left or right, but I stay horizontally right here at 0. And 3 is the y coordinate, is a positive number, so I will move along the y-axis, but up by 3 units. So 1, 1, 2, 3. This will be point P2. Point P3. The x coordinate is 5, the y coordinate is 2. So first I move to the right horizontally 5 units, and I will, from there, I'll go up by 2. So horizontally by 5 units is here, up by 2 units is here. Moving horizontally, vertically, parallel to the y-axis, horizontally by 5, vertically by 2, and this is point P3. It's fairly easy to plot points. -2, 0. -2 is the x-coordinate, is a negative number, so I'm moving 2 units horizontally to the left of 0, and the y-coordinate is the point 0, so I'm not going up or down because the y-coordinate is 0, so I'm just staying horizontally 2 units to the left, so that's just point P4. And point P5 is -3, -4. So to the left horizontally by 3 units, down by 4 units. Horizontally 3 by 3 units, down by 4 units. Again, horizontally to the left because it's a negative x, and vertically down because it's a negative y. So -3, -4, that's where point P5 lies. So this is how you actually plot points. All right, once you know how to plot points, then as I said before, a collection of points connected together in the Cartesian plane will make up the so-called graph of an equation. Which points do we pick? And now we know how to plot points. We know what the Cartesian plane is. So we'll plot points, connect them together, and then that will make up the equation of a graph. These equations of graphs are individual to the graphs. They depend on, these graphs are individual to the equations. Depending on what the equation is, that's what the graph will look like. So first, let me just give a definition. What do we mean of a graphical solution to an equation? And then we'll attempt to graph some common equations. Okay, so here's the definition. A solution to an equation in two variables, a graphic solution to an equation is a pair of real numbers. So such that what? Let me just write this down. So a solution to an equation in two variables is a pair of real numbers a particular pair of real numbers, such that when you take these real numbers and you plug them into the equation, you get a true statement. So that pair would be a particular solution of this equation. So, such that when plugged into the equation, we get a true statement. Okay, so not just any random pair of real numbers is necessarily a solution to a given equation. The idea is that that pair would be a solution if the pair satisfies the equation, meaning it turns the equation into a true statement. All right, so what do we mean by the graph of an equation, as I said before? So the graph of an equation would be the collection of all points, the collection, not necessarily only one pair of points will satisfy the statement or will turn the equation into a true statement. In fact, it could be infinitely many such pairs. So the collection of all of these, if you plot them and connect them together in Cartesian plane, will make up the so-called the graph of an equation. So would be the collection of all pairs that are solutions to the equation. Okay, so let us do some examples. I will attempt to graph these common equations that I mentioned before. So let's start with the simplest of them all. So graph the equation. Y equals to x. So the first thing you do is you create a table of values. So you take some random x's, values for x, you plug them into the equation, you get the value for y, depending on what the equation is. Then you take the pair xy, you plot it in the Cartesian plane, and then you connect them all, you get the graph. So the first thing you do is you create a table of values. Um, all right, so this is the value for x. Here we'll write the value for y. I'll pick some random x's, I plot them in this formula, and I'll get my y's. Formula is pretty simple. Whatever x is, that's what y will be, because my equation is x equal to y. So let's say I have the point -4. Since x is equal to y, then y is also -4. Then let's say -3, then y is -3. -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. Okay, so I will plot the points -4, -4, -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. I'll plot them all in the Cartesian plane, and then I connect. Plot and connect. So let's do this. I'll draw my axis. I plot the points. I'm not going to write the numbers, so the picture does not look very heavy and confusing, but basically every square is 1 unit. So this means 1, 2, 3, 4, and so on. All right, so let me plot -4, -4. I'll go -4 to the left, -1, -2, -3, -4. And I go vertically down also by -4. 1, 2, 3, 4. So -1, -2, -3, -4, -1, down vertically parallel to the y-axis, -1, -2, -3, -4. So that would be my point -4, -4. Okay, next I'll plot point -3, -3. So to the left by 3 units, down by 3 units. So -1, -2, -3, down, -1, -2, -3. This is my point -3, -3. Similarly, -2, -2, -1, -1, 0.00, 0.11, 0.22. You might say, should you continue plotting more points? Yes, if we wish, we can do that. But I have enough points to sort of have an idea what this will look like if I was to connect them all. So there is no good number as to how many points do you need to create, to plot in order to get a very good idea with it. Of course, the more points you plot, the better the idea you get for the graph of a function. But in our case, it's more than enough. So if you were to collect all the points, you'll see that the graph looks like this very straight line passing through the origin. Of course, you're going to have to indicate the arrows here because the line will continue to infinity on both directions. In fact, any point on that line will be a solution to your equation. All right, here's another example. This is example. This was example 1. So create a table of values and then plot a connect depending on what equation we're talking about. So the second example would be y equals to x squared. All right, so again, we create the table of values. X and y. I'll take some random x's, I plot them in my equation, I see what y is, and then I'll plot the points. So -3, -2, -1, 0, 1, 2, 3 are all good candidates. So if you take -3 and you plot it here, meaning -3, so y would be equal to -3 squared, that is equal to 9. This is -2 squared, that would be equal to 4. -1 squared, that would be equal to 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So we're going to plot points -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Let's plot all of these points. So now we plot and connect. Plot and connect. And see what we get. So let's draw our Cartesian plane. Okay. Okay. And again, 1 square is 1 unit, so I don't burden the picture much. So minus 3, 9. To the left, horizontally by 3 units, up vertically by 9 units. So minus 1, minus 2, minus 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is point minus 3, 9. Okay. Next one is point minus 2, 4. So to the left horizontally by 2 units, up by 4 units, minus 1, minus 2. Minus 1, minus 2, minus 3, minus 4. This is point minus 2, 4. Point minus 1, 1 is this point here. Point 0, 0 is here. Point 1, 1 would be here. Point 2, 4 would be here. And point 3, 9 would be this point here. This is enough to, so there is no reason to think that you shouldn't attempt to connect always points in a straight line, because they may not lie on a straight line, as such is the case here. So if you are trying to connect those points, you will get the following graph. Again, I'm putting the arrows there to indicate that you can extend those two curves to infinity. So any point on this curve, whether it's somewhere here or here or here or here, whatever it is, it's a solution to your equation. Such a type of curve, we call it a parabola. So this is otherwise known as a parabola. Okay, so let us do another example. That is the equation y equals to x to the third. Then we'll plot, take some x's, find the corresponding y's according to the formula we have, meaning the equation we have, and then we'll plot the points, and then we'll connect at the end. All right, so let us do the table. All right. So I'm going to do minus 2, minus 1, 0, 1, and 2. That should be enough. So minus 2, so this is your x and this is your y. Minus 2 to the power 3 turns out to be equal to minus 8. Minus 8. Minus 1 to the power 3 is minus 1. 0 to the power 3 is 0. 1 to the power 3 is 1. 2 to the power 3 is 8, but probably I should just add 3. 3 to the power 3 is 27. I could have put minus 3, that would be minus 27. So, oh, let's see. Uh, all right, let's try to uh, -2, -8. So -2 to the left and down by 8 units. So -1, -2, down by 8. 1, 2, 3, 4, 5. So 1, 1, 2, 3, 4, 5, 6, 7, 8. So that's point -2, 8. -1, 1 is this point here. 0, 0 is this point here. 1, 1 is this point here. 2, 8 would be this point. And 327 would be somewhere here if I had more. Okay. So let's say point 327 is somewhere there. Again, I'm running out of space. All right, so let's connect this. If you were to plot more points, you'll see that the general shape of the graph is exactly that. So that's the general shape of the equation y equals to x to the third. All right. Yet another common but yet interesting equation. That would be the equation y equals to the square root of x. Let me remind you, by definition, what do we mean by the absolute value of x? By definition, the absolute value of x will be just the number x if x happens to be positive, and it will be minus x if x is negative. Okay, so again, plotting points or making a table rather, and then plotting points. So this is x, and this is y equals to the absolute value of x. So let's say -3, y would be to the absolute value of -3. Absolute value of -3 is just 3. -2, absolute value of -2 is just 2. -1, absolute value of -1 is also 1. 0, absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. And absolute value of 3 is also 3. So I'm going to plot points -3, 3, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3, and then connect them. Okay, 1, 2, 3, 4, and so on. -1, -2, -3, -4, and so on. -1, -2, -3, -4, and so on. 1, 2, 3, 4, 5, and so on. All right, minus 3, 3. Minus 3, 3 would be this point here. Minus 2, 2 would be this point here. Minus 1, 1 would be this point here. Let me just draw the perpendiculars for clarity. 0, 0 is this point here. 1, 1 is this point here. 2, 2 is this point here. 3, 3 is this point here. That's more than enough. This suggests rather a straight line, like a V shape. So if you were, oops. All right. That is the graph of the absolute value of x. It's a V-shaped graph. All right, moving on. It's important that you know how to graph common functions. And remember what the graphs look like, as we shall refer to them a lot in the following lectures, and we're expected to know what the shapes of the graphs of these common equations look like. All right, so moving on to the next example. Y is equal to the absolute value of x. All right, sure, again, we'll do the table and plot values. So if x is, I don't know, 0, 1, 2, 3, 4, and 5, you might say, why you're not considering some negative numbers, just like you did with these other examples? Well, if you look at the equation, it is the square root of a number. It is the square root of a number. I cannot plot negative values for x because the square root of a negative number is not defined. So the type of numbers that you try to plug in and get y, it has to be in conjunction with the way your equation is defined. So as I said before, you cannot take the square root of a negative number. That's why I'm not giving x negative values. All right, so the square root of 0 is 0. Square root of 1 is 1. Square root of 2 is approximately 1.4. If you plot that in your calculator, the square root of 3 is approximately 1.7. The square root of 4 I know is equal to, square root of 4 I know is equal to 2. And square root of 5, it's approximately 2.3. And if you do one more, square root of 6 is approximately 2.4. So I'll try to plot these numbers. Let me consider larger intervals here. So 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and so on. All right, so let's see. 0, 0 is here. Square root x is equal to 1, and y is equal to 1. It is this point here. When x is equal to 2, square root of 2 is 1.4. So that is somewhere here. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4. So square root of 2 is about 1.4. Square root of 3, let's say it's slightly larger than square root of 2. So 3, let's say 1.7 is somewhere there. 4 is equal to, 4 is connected to 2, because square root of 4 is 2. 5 is, well, we're going to x equal to 5 and y equals to 2.3. Let's say 2.3 is somewhere here. And 6, let's say, is 2.4. The y is 2.4. So if you were to connect this, I didn't do apparently a good job, but I'm gonna clean this up. Okay, so this looks a little better. That's the graph. That's the graph of the square root of x. The general shape of the graph of this equation. Okay, so much for the graphs of common equations. These were some examples. So the idea is the only tool that we have so far is, here's the equation. I take some x's, some random x's, always in conjunction or keeping in mind what the equation is. I'll plot them in my equation. I get a pair. I plot all the pairs. I connect them. I get the graph. All right. So now suppose that you have an equation and you have graphed it, and the graphs. There is no fast way to tell what the graph of a function is. You actually have to graph it. But a graph of function, nonetheless, it's somewhere in the Cartesian plane, and the curves may be looking in certain ways, but it is possible that the graph of a function will cut the x and the y axis along the way somewhere. So if a graph of a function will cut the x-axis somewhere, we will call that point, the point in which the graph of a function intersects with the x-axis, we'll call that an x-intercept. And the point where the graph of a function will cut or cross the y-axis somewhere, we'll call that a y-intercept. Identifying x and y intercepts will be very important. It will be a very important tool when it comes to graphing certain equations. So if you can identify immediately what the x and y intercepts are, you already will have at least 2 points on your graph, and then you can build from there. So having the graph or not, it's good to be able to identify the x and the y intercepts. But first, let me just write the definition for x and y intercepts, and then we'll do some examples. All right. So x and y intercepts. Definition. The x-intercepts, by the way, the graph of a function, the graph of an equation, may cut the x-axis more than once. So that's why in this definition, I'm referring in plural, the x-intercepts. It's not only one x-intercept that the graph of a function of an equation might have. So the x-intercepts are all the x values where the graph cuts the x-axis. Cut the x-axis. The y-intercepts are all the y values where the graph cuts the y-axis. Cuts the y-axis. All right. So let's see. Let me just draw some pictures. Let's say that I have the graphs. I already know what the graphs of some equations look like. So let's say that I have a graph that looks like this. Okay. And let's say that I have a graph that looks like this. Okay. All right. So here are the graphs for figure 1 and figure 2. And I need to identify the x and the y intercepts simply just by looking at the graph. As the definition indicates, the x-intercepts are the points where the graph cuts the x-axis, and maybe more than one, and the y-intercepts are the points where the graph cuts the y-axis. So according to the definition, by the way, this arrow here indicates that this line goes to infinity and it gets very, very close to the x-axis, but it doesn't necessarily touch the x-axis. That's what this arrow indicates here. We'll talk more in details about this phenomenon a little later in the course. Okay, but as far as we're concerned from figure 1, there is no x-intercept. It's only one y-intercept. There's only one point where my graph will cut the y-axis, and this is the point P1. and that is the y-intercept. Okay, so what do you think are, well, I don't know what do you think, but I can tell you what the coordinates of the point P1 are. Since P1 is the point where the graph and the y-axis meet, it means that this point lies along the y-axis, is on the y-axis. So the x-coordinate of any point that is in the y-axis is always 0. So x-coordinate of an y-intercept is 0, and the y-coordinate is some number. I don't know what that number is, it's irrelevant, but let's call that number y1, since I call the point p1. Okay, so let's identify the x and y intercepts, if any, in the figure 2. Here is a point where the graph cuts the x-axis, so that is an x-intercept. Here is another x-intercept. Here is yet a third x-intercept, a fourth x-intercept, a fifth x-intercept. And there is only one point that is a y-intercept. So P1 through P5 are x-intercepts, and P6 is the y-intercept here. And P1 is just the y-intercept in this figure. All right, all points, so x-intercepts are points that after all lie on the x-axis. So the y-coordinates of any point that is on the y-axis, in the x-axis, the y-coordinate will be 0. The x-coordinate of any point that is in the y-axis is 0. So point on the y-axis has a 0 x-coordinate, point on the x-axis has 0 as a y-coordinate. Okay, so let me just write this down. X-intercepts always have y-coordinate equal to 0. And y-intercepts always have x-coordinate equal to 0. Okay, here's the third figure. Let's say you have this graph, and this looks like a circle. So let's say that, as we will learn this very soon, the equation of a circle looks, it's of this form. So equals to 16. Let's just say that, where the radius here is equal to 4. So this is a given graph. How to graph such a thing we'll learn in the next 2 lectures or so. But for the moment, let's say that you have this graph. Identify the x and the y coordinates. I'm telling you that the radius of the circle is 4. So the x coordinates, the x-intercepts are point P1 and P2, and the y-intercepts are points P3 and P4. Okay, since you know what the radius of this circle is, you can easily tell what the coordinates of x and y intercepts are. So P1 and P2 are x-intercepts, and P3 and P4 are y-intercepts. So just because the radius is 4, it means that this distance from here to here is actually 4. This distance from here to here is 4. This distance from here to here is 4. And this distance from here to here is 4. So since P1 and P2 are lying along the x-axis and they are 4 units away from 0 horizontally, P1 is to the left of 0, P2 is to the right of 0, but they are the same distance from 0, and that is 4 units. It means that the coordinates of point P1 should be, keep in mind, an x-intercept, the y-coordinate is always 0. So since P1 is 4 units away to the right of 0 horizontally, it means that the x-coordinate is 4 and the y-coordinate is 0. P2, the x, well, it's to the left of 0 horizontally, still is 4 units away from 0 horizontally to the left, which means that the x-coordinate of P2 must be a negative number, negative 4. 4 units away from 0 to the left of 0 means minus 4. Again, the y-coordinate is 0, according to this rule. P3 and P4, they both lie along the y-axis. So their x-coordinate is 0. And both of them are vertically 4 units away from 0, one up and one down. So the one that is up should be the positive 4, the one that is down should be negative 4. So given a graph, it's not difficult to identify where the x and the y intercepts are, given that you know what the graph looks like, or you already have the graph. So now the question is it possible to find the intercept if you don't have a graph available? So if no graph is known, can you still find out what the x and the y intercepts are? The answer is yes. And graphing a function, generally speaking, is not an easy deal. So the more points you identify of your potential graph, the better. And knowing x and y intercepts, it's always useful. So in your quest for graphing an equation, knowing beforehand which points will be on the graph certainly helps. And x and y intercepts are such points. So now, let's find the intercepts if no graph is known. So we want to now find intercepts if no graph is known. Okay, so we did say before that x-intercepts always have the y-coordinate 0 and y-intercepts do have the x-coordinate 0. That's what we're cashing in to actually find x and y-intercept if we have the equation but not the graph. Okay, so to find the x-intercept, we set y to 0 because I know the y coordinate is always 0. We set y to 0. And solve for x. For the y-intercept, to find y-intercept, we set x equal to 0 and find y. Okay, so now let's take the same last example for this equation. Okay, so let's say I don't know what the graph looks like. I don't know if it's a circle or not. I have no idea what the graph looks like, but I do have the equation. And the equation is this: x squared plus y squared is equal to 16. And I wish to find x and y intercepts. Okay, so as we said before, to find the x-intercept, so for the x-intercept, I will set equation to 0. I'll set y to 0. We'll let y be equal to 0, and then we have x squared plus y squared, or 0 squared, is equal to 16. I'm setting y to 0 and I'm solving for x. So this means that x squared is equal to 16, or this means that x itself is equal to plus or minus square root of 16, not just the square root of 16, but plus minus. That's the same as saying as x is equal to plus or minus 4. So, points 0, 4, and 0, minus 4, I'm sorry, the other way around, minus 4, 0, and 4, 0 are the x-intercepts. And that corresponds with what we got before. These are the points that we got before just by looking at the graph and knowing that the radius is 4. Okay, so for the y-intercepts, we set x to 0. We set x to 0 and solve for x and solve for y. So 0 squared plus y squared is equal to 16. This means that y squared is equal to 16. This means that y itself is equal to plus minus the square root of 16, or equal to plus minus 4. So the y-intercepts, since I know that the x-coordinate for those is both 0, will be point 0, minus 4, and 0, 4, and that corresponds with the points that I got when I knew what the graph looks like. All right. Here's another example. Here's another example. Let's say you have the equation y equals to square root of 2x minus 1. Again, find the intercept. You don't know what the graph of this looks like. We need to find the intercepts. Okay, so for the x-intercept, I'll set y to 0. Okay, so 0 equals to the square root of 2x minus 1. You know from college algebra that if you have an equation that involves a radical, a square root, to get rid of the radical, you need to square both sides. So I need to square both sides here. So 0 squared is equal to the square root of 2x minus 1 squared. 0 squared is 0. Square root of 2x minus 1 squared is just 2x minus 1. This is now very easy to solve. From here, uh, I will add -1, I'll add 1 to both sides. So 1 equals to 2x minus 1 plus 1. This is plus 1 minus 1 is just 0. So 1 is equal to 2x. To get x by itself, I divide both sides by 2. So 1 over 2 is equal to 2x over 2. And this means that x itself is equal to 1/2. So the x-intercept is point half 0. That is your x-intercept. Okay. For the y-intercept now, for the y-intercept, I'm going to set x to 0. So for the y-intercept, I will set x to 0. All right, when you set x to 0, you get what? You get y equals to 2 times 0 minus 1. 2 times 0 is 0. So we end up with y equals to minus 1. But square root of minus 1 is not defined. It makes no sense. So this makes no sense. So then what? This means that actually there is no y-intercept. X and y intercepts don't necessarily have to exist for the graph of an equation. It all depends on the equation. So in this case, we have x-intercept, but we have no y-intercept. So this means that there is no y-intercept. Okay. So much for this lecture. Once again, look over section 1.1, go over homework number 2, look over the lecture notes, and surely we can discuss in a Zoom meeting together if you don't understand something about the lecture or something about what's in the book or whatever clarifications that you might need. So long until next time.